Okay, so the last theorem we tried to prove for last week is that for any square matrix A, the determinant of its transpose of A is equal to the determinant of A. And we also note a fact that A is invertible, even only if its transpose is invertible. And the reason is here. We can just express the inverse of A transpose to be the transpose of the A inverse. By checking everything here. Alright, and so we have two cases to study. First of all, A is not invertible. Right? Now from this fact, A is not invertible, then A transpose is also not invertible. So that the determinant of A transpose is equal to 0, is equal to the determinant of A. Because we proved in our previous study that by theorem 4.1.4 plus 1. So prove that. In this theorem, it says that the determinant of the square matrix is non-zero if and only if the matrix is invertible. So that if a matrix is not invertible, then its determinant is 0. So this one is okay, right? So we established the identity already because both of them are equal to 0. So now we go to case 2. Now case 2 is that A is invertible. Now, the reduced actual form. Alright, so reduce the raw actual form of A is the identity matrix. Right, we all know that because A is invertible. So the reduced actual form of A is identity. And how do we reach to this reduced rational form? Alright, so there exists a sequence of elementary matrices. Alright, so the matrices will be E1, E2, etc. up to EK, such that EK E1, E2, E1A equal to A. So we can reach to the reduced rational form by row operations, and it is equivalent to saying that we multiply the matrix A by elementary matrices from the left. Okay, so we have a sequence of elementary matrices. Alright, so that's A and is equal to E1 inverse, E2 inverse, and the EK inverse. and F I equals to EI inverse is also an elementary matrix. Okay, for OI. Okay. These are facts we all know in chapter 1, that the inverse of elementary matrix is also elementary matrix. And then now, A transpose is equal to F1, F2, Fk transpose, right? Because A is product of F1, F2, of Fk, and this is Fk transpose, F2 transpose, F1 transpose. Okay, so the determinant of AT is the determinant because AT is product of K matrices. So by the product formula, so we have this is Fk transpose, the determinant of F2 transpose, determinant of F1 transpose. Okay, but we have proved a lemma that for elementary matrices, its transpose, the determinant of its transpose is equal to the determinant of itself. So that this is the determinant of Fk, the determinant of F2, determinant of F1 by lemma 4.2.3 we proved the last week, and so with that. And so now we can change the order. The determinant of Fk, right? And by because they are scalars, right? So we can change the order of the product. And by the product formula, this is just okay, the determinants of the product of these elementary matrices. But as we know, this is determinant of A. And so with that. So lemma 4.2.b are special cases of this theorem. Because in that lemma, we show that when A are elementary matrices, this identity is valid already, right? So we show that. And we take this fact as an advantage to prove the general case when A is invertible. When A is invertible. Okay? And then we also resort to the Gaussian Jordan information, right? Choose operations. Do it. Any questions? All right, so we have the theorem gives us quite a few consequences. The first one is that the rows of A transpose are the columns of A. Right? So this is the first observation. Okay? The rows of transpose A is just the columns of A. Okay? So they are. Okay? So all properties okay, of the determinant function. Det from to R. I have a version for columns. For example, determinant of A is linear on any column of A. Okay. So that if we know a column of A is a linear combination of two columns, of two vectors, then we have linearity. Okay. So that because for determinant function, we have a linearity on any rows, but now we have linearity on any columns of it. And swapping two columns of A. So if we swap two columns, A, P, and G, swapping two columns of A will change the sign of the determinant value of the determinant value. Okay? So swapping for rows, if we swap two rows, then the sign of the determinant has to change. But now, if we swap two columns, then the determinant value will change the sign. Also, by scaling a column of A by a scalar alpha, then the determinant will be multiplied by alpha. Okay. One more. When adding a multiple of a column of A to another column of A, the determinant will not change. Will not change. Okay. So, adding a multiple of a column of A to another column of A, scaling a column of A, swapping two columns, they are called elementary column operations, corresponding to elementary row operations. Okay. So now, when we do the elementary column operations, the effect will be the same as we do the elementary row operations on the determinant value right now. Okay? So this fact gives us a lot of degree of freedom to deal with determinants of square matrices. Because we can do count operations as well as row operations. Questions? And we will explore this next later. Alright, so we give a name 4.2.C. Now consider a spatial square matrix A. Okay, where n is n minus 1 times n minus 1 matrix, right? So consider a spatial types of matrix here, and A is n by n, but it can be decomposed blockwise, like this one. So this is just the scalar one. And we have n times 1 minus n minus 1 times n minus 1 matrix, square matrix right here. And this is all zero entries there. Okay. Then the determinant of A is equal to the determinant of n. So the purpose is that originally we have to compute determinants of n by n, right? So this is a bigger matrix. But the truth is that this determinant is equal to the determinant of a smaller matrix with dimension n minus 1 times n minus 1. Alright, so the proof. So we let U be the reduced row echelon form of M, by applying a sequence of elementary row operations on M. i.e., we have EK, that is E1, E2, E1, and M equal to U. Right. So suppose U is the reduced row echelon form of M. Okay, and where E1, E2, to the third, EK are n minus 1 times n minus 1 elementary matrices. Okay, now, so then the block 1, 0, 0, U. Now, So this is an M times M matrix. Now then is in the reduced row. Echelon form. By applying a corresponding sequence of elementary row operations on A. i.e. Okay. You can think about this is block diagonal matrices, right? And so when you multiply these two block diagonal matrices, the result is 1 times 1, 0, 0, and then E1 times M. Okay? So just like a diagonal matrix, you multiply diagonal matrices in the same. So block diagonal matrix, you can do it blockwise. Do you have any questions about this identity? Because that the result is okay? Is that the product is just this block diagonal matrix. And here this is equal to here. Okay. Any questions up to now? And you can see that they are elementary matrices. They are M by N elementary matrices. When E1, E2, EK are n minus 1 times n minus 1 elementary matrices. Okay. All right, and then now determinant of is equal to determinant of EI. What? Let's go to C. If the EI corresponding to replacement, okay? Then we have three types of elementary row operations. One is replacement. Second is scaling by a non-zero scalar. So the one is the exchange, swapping, right? Right. So if EI here, if EI is about replacement, then this is also an elementary corresponding to replacement too. Okay. And so this is a replacement. But for replacement, the determinant is always equal to 1. So this is 1, this is 1, so they are equal. Okay. For the scaling, if EI is the scaling, corresponding to the scaling, right, then this is also corresponding to the scaling of a row. Okay? And for scaling, the determinant just equal to the scalar alpha. So they are the same, because they are all equal to alpha. Finally, for swapping or for row exchange, if EI corresponding row exchange, two row exchanges, then here we also have two row exchanges. And their determinant will all equal to -1. So they have the same value. Okay, so because they corresponding to the same type of elementary operation. As I just explained. Any questions? So actually, once again, if M is elementary matrices, then this is true, okay? Again, once again, it's quite easy to check, right? This is true for M to be an elementary matrix. And so actually we apply the same technique. So that for general situation M, we just write down the reduce the row echelon form. Any questions up to here? All right. So and we also know that M is invertible if and only if A is invertible. Since the inverse is okay, so you can check. Now if M is invertible, it means M inverse exists. Yeah. Then A has inverse which is equal to the formula. Okay, so on case 1. M is non-invertible. Then A is non-invertible too. Okay. Right. So when M is non-invertible, A is non-invertible. such that the determinant of A is 0 is equal to the determinant of M, of course. So we establish nonunity once if M is non-invertible. Alright. So when M is non-invertible, then we establish that because they are determinants 0. Case 2, M is invertible. Then U is identity. Right? So U is identity. And is reduced rho echelon. Okay. This, of course, must be true. Why? Because when M is invertible, A must be invertible. So the reduced echelon form of A must be identity. We all know this fact. But we can get this from the one again, right? So okay. Okay, so now we have determinant of dk, the determinant of E2, determinant of E1, determinant of M equal to determinant of from here, right? So we take the determinants. So this is determinant identity. Okay, this is 1. Okay. So from this, because the U, we know because M is invertible, so the reduced diagonal form of M is identity. Okay. And by our axiom number 1, the determinant is 1. Okay. Now determinant. Similarly, we have this product. So determinant of 1, 0, 0, okay. Determinant of 1, 0, 0, 2. Determinant of 1, 0, 0, 1. Determinant of okay is equal to determinant of I and equal to 1. Okay. From this identity. Okay, so we have that. And then we take the region here and here. Okay, so we divide this equation by this equation. And then remember, they are the same, right? Because we know that. So they can cancel. And so cancel. Alright? So we have determinant of M, determinant of A is equal to 1 divided by 1, which is 1. And so determinant of A will be the determinant of F. Like that. You can see even though the proof is long, right? But the idea is simple. It's simple because we always use the Gaussian elimination. So we apply elementary law operations. That's the key idea. So we can establish the identities, and then we can apply the product formulas for determinants. Okay. So product formula of determinants so useful, right? We can apply them in many places. Yeah. Questions? Okay. All right, so now we will develop the technique to find determinants. And then the final goal is to prove that the determinant function by given three axes exists and unique. This is our final goal for this chapter. But in the meantime, we will develop many useful properties. Now, so by removing the ith row and the jth column of an n times n matrix A. Right? So A is A11, A1, A minus 1, A1J, A1J plus 1, A1N, AI1, Aij minus 1, Aij, Aij plus 1, Ain, okay. And the last row, AM1, J minus 1, J plus 1, An. Okay, so we just remove the ith row and remove the jth column. And suddenly, we obtain an n minus 1 times n minus 1 matrix. And the name will be M-I-J-A. So say that this matrix is from the original matrix A by removing the ith row and the jth column. So M-I-J-A 1 should be A11, A1J minus 1, and then A1J plus 1. A1N. Okay. And So we have A, I minus 1, 1, A, I minus 1, J minus 1, A, I minus 1, J plus 1, A, I minus 1, and the N. The next one is A, I plus 1, 1, A, I plus 1, J minus 1, A, I plus 1, J plus 1, A, I plus 1, N, A, N 1, A, N, J minus 1, A, N, J plus 1, A, N, N. Okay. Okay. I took my time because I want you to have a very solid impression about how we extract this submatrix from the original matrix A. And we use M because it's minor, because it's a minor of A, because we extract this smaller matrix from the original matrix by removing the ith row and the just column. And I want you to learn how to write down the entrances. Okay, I hope you learn how to do it. Okay, even though it's look like a teacher, but it's very useful. You have to develop yourself to have the ability to write something like that. Originally looked complicated, but really it's not complicated. Alright, so which will be called the ij minor of A. Alright, so M is a minor, ij is a pair, ij is okay. not good looking. I tried I, not good. Okay, great. So now, so if there is no ambiguity within a context, we may write Mij or Mij. Alright, so if we know what is A, what is the original matrix A is, then we just write Mij instead of Mij. Alright, so now why we need to consider the ij's minor of a square matrix. Well, so we take an example of calculating the determinants of a 3 by 3 square matrix. So suppose A is A11, A12, A13, A21, A22, A23, A31, A32, A33. Okay, yes. Now, so we know that the first row of A is A11, A12, A13, and it's a linear combination of A11, 1, 0, 0, plus A12, 0, 1, 0, plus A13, 0, 0, 1. Okay, so the first row is a linear combination of 3 row vectors. So by linearity on the first row, alright, so now the determinant of A becomes to A11, determinant of 1, 0, 0, A21, A22, A23, A31, A32, A33, plus A12, determinant of 0, 1, 0, A21, A22, A23, A31, A32, A33, plus A13, determinant of 0, 0, 1, A21, A2. Okay, so by the linearity on the first row. Okay, so we have linearity. So we do that. Now, we apply row operations, replacement row operations. So by the replacement mode, we can cancel these two, right? We can cancel these two. And when we apply the replacement operation, we will not change the value of determinants. So that we will eliminate these two. Also, by this one, we can the pivot, we can eliminate this one. We can eliminate this one by elimination. All right. So now we have A11 determinant of 1, 0, 0, 0, 0, and A22, A23, A32, A33. Now you will see the connection rate, right? And the A12 determinant of 0, 1, 0, A21, A2, 0, A23, A31, A33, okay? And A13 determinant of 0, 0, 1, A11, A21, A22, 0, A31, A32, 0. Okay, that way. Okay? But we want this form. How do we get to this form? Well, you can use column operations now. So this is the first time we use column operations. We exchange the first column and the second column. Right? So we exchange them. But once we exchange, the sign should change. Similarly, we can exchange we can exchange this one goes to here, so the third one goes to the second one, and then goes to the first one. So we do the row exchange twice. But when we do twice, then we change the sign and change the sign again. So minus 1 times minus 1 equals 1. Okay, so we have A11. A minus plus minus 1, A12 determinant. Okay. So we change the first and the second column. So we multiply with minus 1. And the plus A13 and determinant okay? Yeah. And for the to and now M11. So this matrix, this submatrix here, is obtained by removing the first row and first column of A. Okay, so you remove the first one. So this is the 1 1 minor. And it's 1. So I 1 plus 1 is 1. And this is 1 plus 2, A12. Determinant of is M12. So this is obtained by removing the first row and the second column. And finally, 1 plus 3 3. Okay. So they are matching, right? 1 plus 1 is A11, 1 plus 2 A12, okay, and A13, 1 plus 3, and M13. Average is just perfect. Perfect, yeah. Alright, and now we can apply our lemma. So that the determinant of this spatial 3 by 3 matrix becomes to minus 1, 1 plus 1, A11, determinant of M11, plus minus 1, 1 plus 2, A12, determinant of the minors, 1, 2 minor, and plus minus 1 plus 3, A13, determinant of the 1, 3 minor. Okay, so the computation, it seems a long story, right? We want to compute the determinant of a 3 by 3 matrix. And it turns out that it's just a linear combination of determinants of 2 by 2 matrices. So we reduce the order of matrix in the computation of matrix of the determinant. So this is expansion. Any questions? Oh. All right. So let's take a break up for vector expansion using those. And I believe the author does not give any proof at all. Okay? But now we have the ability to prove it now. Okay, so we let A be an n times n matrix. Then the determinants of A can be written down minus 1 I plus j aij determinant of n ija. Okay, and that is equal to aij and the cija. Where cija is defined to be minus 1 raised to the I plus j power and the determinant of minus is called the I j covector of A. Alright, so compare with that. This is a generalized formula. Maybe I just draw I. Be more specific. I can be any row, okay? So just covector expansion using row I. In here, we have the covector expansion of using the first row 1, okay? But in general, we can expand. We have an expansion formula using an arbitrary row, any row. Okay? So you can see the entry. This is AI1, AI2, AI3, so that we have entries in the ith row. And this is the corresponding minus of A, ij's minus of A, etc. And we define the covector Cija to be the determinant of the ij's minor multiplied with sign. This sign depends on ij. Okay? On ij. So any questions about the statement of this theorem? Alright, so if there's no problem, then I will move on to give a proof. The proof is follow the similar idea in the example we work out. And you will see more systematically why we have this sign. And the power y, the exponent is I plus j. Okay. The proof. Now the ith row. Okay, of A can be expressed as a linear combination of standard unit row vectors E1, E2, etc. of the Vn, i.e. Ri is written as I 1, 0, 0 plus A I2 0 1 0 plus plus A I N 0. So this is AI1 1 plus AI2 plus AIN. Right. Now, by the linearity, of the determinant function on the I0, so we have that the determinant of A is equal to AI1, determinant of R1, E1, Rn, plus AI2, determinant R1, E2, Rn, plus plus AIN, determinant of R1, En, Rn, and we will call this matrix defined to be AI E1. Okay, and this one defined to be AI E2, and this matrix defined to be AI EM. And why is that? AI is that so this is the matrix obtained from A, from A by replacing the I0 of A with E1. Okay, so here is that this is a matrix obtained from matrix A, okay, by replacing the I0 of A with E1. And here is the matrix obtained from A by replacing the I0 of A with E2, etc. Okay, so we use this notation. Okay, and so now we can write it down to the Aij, determinant of AI replaced by Ej. Okay? Is that okay for now? So the determinant of A becomes to a linear combination of determinants of rows matrices obtained from the original matrix A by replacing the ith row of A with different standard unit row vector J from 1 to n. Is that okay? The notation. Now we will work on the determinant of this matrix. Now, so by replacement, row operations on the matrix AI EJ. Okay, so this C A11 A1J A1N 0 1 0 AN1 ANJ ANN. So the ith row of A is replaced with the EJ, and then here is the jth column. Okay, so AI of EJ is this matrix. Okay, and now we can do the row operation. How to do that? The replace row is to use to cancel all the entries in all other entries in the jth column, right? So we can cancel all of them. So we can eliminate all of them here, right? So that this matrix will goes to P IJ, which is A11 0 1 A1N 0 A1 0 A1N. So we have right. So the ith row has 0 entries except at the jth position, and the jth column has 0 entries except at the ith row. Okay, so we have 0 0 0 1 0 0. We have 0 0 0 1 0 0 0 here. All right. So by element row operations, we turn the AI EJ go to BIJ, and the determinants of this matrix is equal to the determinants of this matrix. Now we will move 1 to the top here. So our object is to move 1 toward here. How can we do that? First of all, we can move the ith row 1 by 1 to the top row, right? By how many exchanges? I row exchanges, right? Right, up to here. And then we can move this go to here. by j column exchanges. Right? So before that, let me write down so that determinant of A is equal to here from 1 to n aij determinant of Bij. Alright, sorry. Let me use the soup. Bij. Alright, now after doing minus 1, sorry, I minus 1 row exchanges, not I exchanges, and j minus 1 column exchanges. So we have Bij, right? So we have 1 here, 0 here, 0 here, and we have M, I, J, A. Right? So when we move up and move left, we have 1 here, so and then 1 goes hit there. So 1, 0, 0, 0, 1, 0, 0, 0. And then with the relative location of A11, A11, they are not changed. So after that, it seems like we just remove the ith row and the jth column. So that is the Mij. Right? It's just like we remove this row and this column. So we have Ij. And so that determinant of Bij equal to minus 1 I minus 1 plus j minus 1, and determinant of 1, 0, 0, M, I, J, A. Okay, so that is. And this is I plus j, because minus 2 is 1. Okay, so you can just take and determinant. So this is what. And by our lemma, this is determinant M, I, J, A. By lemma, open to point. We just put C. Okay, so we mark. Alright, so now determinant of A becomes the summation of j from 1 to n minus 1 I plus j, A I j, determinant of M I j A. Alright, so this is our formula already. This is the and by the definition of covector, where Bij is defined to be minus 1 I plus j, determinant of M I j A is the Ij is the ijth covector of A. Okay, and we have done. So we prove the perpetual expansion for A. Okay? So the tensor of the proof is not complicated. Right? Actually, it's so neat. Any questions? Alright, so we now be able to prove theorem 4.2.5, also called the Cramer's rule. Cramer's rule. Okay. If A is invertible, then the solution to the linear system AX equal to B for any B in Rn is given by Xj equal to determinant of A, J now, J into the subscript instead of the subscript. And determinant of A. Where A, J, B is the matrix obtained from A, right, from A by replacing the jth column of A with B. Alright? So we know if A is invertible, then this linear system is a unique solution. We know that. Alright? So the solution X is A inverse multiplies B. But you have to find the inverse of A, right? Before you can find the solution. But the Cramer's rule gives you a solution without finding the inverse matrix of A. Okay. And so the expression is that it's a ratio. So the solution, the jth component, jth component is that is the determinant of this matrix divided by the determinant of A. And what is this matrix? It's exactly the matrix is the original matrix A, but you replace the jth column of A by B. Okay, so if you like, I can write it the determinant of A1, A j minus 1, B, A j, A n. Right, so we have n columns, right? And the determinant of A is A1, A j minus 1, A j plus 1, sorry, j plus 1 here, A n. Okay, so you can see very symmetric, right? You see that all the columns they are the same. Only the jth column here. The jth column of A has been replaced with B here. So you have to compute two determinants. for each component. So actually, you have to compute n plus 1 determinants, right? One is the determinant of the original matrix A, and then you have to compute the determinant of the original matrix A, but every column has been replaced by B. And then you have n such different matrices, right? And so you have to compute n determinant plus 1 determinant. So in total, you have to compute n plus 1 determinant. N plus 1 determinant. This is called the Cramer's rule. Of course, the solution, the complexity is very high compared with the Gaussian elimination method. Okay, so but it's very beautiful in formula, but it's not good for computation. So it's a very important warning. Don't use this one to compute. Use Gaussian elimination. Okay, always use Gaussian elimination. Proof. Okay, so you can appreciate the beauty of the proof. Okay, now relate identity J X be the matrix obtained from the identity matrix I by replacing the jth column of I with the x column vector. Now then, we have very interesting that A, I, J, X. A, I, J, X is A, so this is E1, Ej minus 1, X, Ej plus 1, En. So EIs are standard unit column vectors. So only the jth standard unit vector has been replaced by x. And so that this is A, E1, A, E, J minus 1, AX, A, E, J plus 1, A, X. But what is that? AE1 is just the first column. This is the J minus 1 column, and this is B. All right, this is B. Remember, our linear system is consistent, always consistent, because A is invertible. Okay, so we know that there is one and only one solution, X. So the solution X exists. If you cannot, because I think I sent you a notice, right, about the importance of the consistent linear system, right? Because if there is no solution and you work on it, then you will get wrong answer, right? So that A is invertible. Make sure that this is consistent. So X is a solution, and now, and A, E, J is A, J plus 1. So that A, N. Okay? So what is this? This is exactly our definition of AJB. Okay? So this is A, JB. This is exactly AJB. Right? Right? So that the determinant of A by the product formula and determinant of I Jx equal to the determinant of A Jb. Right? So we have the relationship here. But determinant of I Jx, what is that? What is this matrix? It's 1, 1, and the xj, 1, 1. And in the just column, we have x1, and this is xn. Right, and it's all 0, 0, 0. Okay, so we have, okay. And this is just row, and here is the just column. Right, so IJX is this matrix. Now, so you can see that we can the just row is 0, 0, 0, 0, xj 0, 0, 0, 0, right? So they are all 0, 0. Alright, so you can think about that. The just row is just xj multiplied with the standard unit row vector ej. So this is xj, determinant of 1, 1, and the 1, 1, 1. And the x1 to the top, xn, and 0, 0, 0, 0. Okay? You have that. Now, you will cancel, right, by replacement, but use the ith row, the just row. You use the just row to eliminate all the entries in the just column. Alright, so this is by replacement. Row operations. Alright, so by replacement operations. Okay, so we have xj determinant of so you cancel this, so we have 1, 1, 1, and all 0, 0. So this is the identity matrix. And so this is xj. Okay, so you know this is xj. This is xj. So finally, xj is determinant of ij x, which is just the determinant of aj p and determinant of a. Okay, so this is our conclusion. Questions? Now, the n times n matrix CA defined to be, so we collect all covectors of A. Alright? So we collect all covectors and put them into a matrix. This matrix is called the covector matrix. Of A. Now we will have a very interesting formula. We call it lemma 4.2.2. For an n times n matrix A, summation of n Aij C Aj A. Right? Now you use the ith row of A, and you use the kth row of the covector matrix. Right? Multiply together to form a sum. Then the sum will be equal to determinant of A if k equal to I. Of course, Ij, this is our formula. This is covector expansion. So this is our previous result, right? The covector expansion, right, on the ith row. So no problem when k equal to I. But when k not equal to I, what happens? 0. This is very surprising. This is a surprising result, right? You can see a surprising result. If we match the product with different rows from the covector matrix, then the result becomes 0. But if we do match k equal to I, then the summation is our determinants of it. So that this is very interesting. Okay, so the proof. By the covector expansion, okay, by the covector expansion using row I, we have summation j from 1 to n, Aij, Cij, A equal to the determinant of A. Okay, so this is true. What when k equal to I. So now we will consider. So now we consider A, K, I. What is that? We replace the original matrix A, right? So the matrix is obtained from matrix A by replacing the kth row with the ith row. All right, so let's see. 1, I again, and this is the ith row. This is the kth row. All right, so for k not equal to I, we consider. Right? So k not equal to I. So for example, this is the kth row, and this is ith row. And then we replace the original kth row by the ith row here. What happened? Because we have equal rows. So the determinants of this matrix is 0. Right? Because equal rows property. So the determinant of AK Ri is equal to 0 for K not equal to I. Okay? Now, by the cofactor expansion, okay, of using row K of AK Ri. Alright, so now we will, because the determinants can be also, again, by cofactor expansion using the case row of this matrix. So we have determinant of A, K, I equal to, what is the case row? The case row actually is Aij, because the case row is just isolated. And we have Ckj, right, of A, K, J, of I. Right? And so this is the cofactor of this matrix, the Kj cofactor, because we expansion the determinants of A, K, I by the case row, and this is the entries in the case row. Okay, and this is called vectors. But remember, when we do the cofactors, we have to compute the minor. So this is summation Aij, and so this is -1, K plus J, and the minor of Kj of AK I. Now, this minor is what? Is to eliminate the case row and the j's column. When we do so, you can see that actually this one is equal to A is the minor, the Kj minor of A, the set. That is the trick. Because we eliminated the case row. Okay? So when we eliminate case row, then the other rows will be the same as the original A matrix. And when we eliminate the jth column, then we end up with the same minor, the same submatrix. So this matrix is equal to this matrix. So that is the key point. Okay? And so now, I'm sorry, I forgot. No, the determinants are. Okay, A. So now, so Aij minus 1 K plus J, determinants of M K J A here. And this is summation Aij, and this is cofactor of Kj. Okay. So determinant is equal to this one. And of course, this is 0. And we have that. So we prove that this is true. When k not equal to 0. All right, and sorry. I put two theorems in the text together. So for any n times n matrix, okay, we have a cofactor matrix, take the transpose, is equal to the determinant of A comes with the linear matrix. Alright, so this is the first result. And if A is invertible, then A inverse is determinant of A and the CA transpose. And so we have a formula for the inverse matrix. And it's easy to see it, just a couple of lines. Okay, so proof. You just multiply. All right? You multiply them. So what is that? The multiplication is that you have row 1, row 2, row 1, okay. Just write down A11, A12, A1n, A21, A22, A2n. AN1, AN2, okay, this is matrix A. The transpose of the cofactor of A is that C11A, C12A here, up to C1A, because we take the transpose. So the first row of CA becomes to the first column of CA transpose, and C21A, C22A, and C2NA. CN1A, CN2A, CNNA. Now, you will see that the first row, right, multiply with the first row of A, multiply with the first row of the CA. Because the first column of the CA transpose is just the first row of the CA, of the cofactor matrix. So when you multiply them, then by using our previous lemma, this is determinant of A. And when you multiply with because the index is different, the second row, the first row multiplied with the second row of the CA become to 0. So we have 0, 0. Okay? And for the second row with the first row, we get 0. And this one is determinant of A. 0. Etc. So we have, in the diagonal term, we have determined A, but the others, they are all zeros. So this is determinant of A and the identity. And then we have that and the proof. Okay? This is by lemma. We just done. This lemma is 4.2.b. Okay, sorry. Okay, so we have the theorem. Okay, so I stop here. And we have the final theorem, that is to prove. Now we are able to prove the uniqueness and the existence and uniqueness of determining function. Okay. But I have no time, so I will do that next week. That will be the final things that I have to do for chapter 4, and then we will move into chapter 5. Any questions? Alright, so if no questions, yeah, I will see you next week.